3 speakers in the list. The first one is Stratos Boutloukos. The name of the talk is the key ingredients into resolving the nature of accretion-powered QPOs in the almost like binaries. So, Stratos, please.
Okay, thank you. Can everybody hear me without microphone?
Unfortunately, we have a microphone.
Okay, so just making sure that everyone can hear me. It's very nice to be here. I would like to particularly thank Gabriel and all the group from Opava to inviting me here. I think it's a very successful conference. I've not been working in the field for a while, but I think there's still some things I can contribute into this topic of QPOs. We have heard a lot of things in the morning, yesterday, and also in the previous session. I would like to add some things about the work that I've done and still relevant, and some new things I've been working on lately. The outline of the talk is basically, after some quick motivation or extra motivation to what we have already heard, what aspects of the Sinus X1 observations that I've worked on are still relevant now, and why, or if they are still unique. Some additional observational evidence that we always have to keep into mind when we think about models. Some arguments for and against the accretion-powered origin of the killer QPOs, which is also part of the talk title. And at the end, I would like to make a connection to low-frequency QPOs and conclude. So, motivation. I guess everyone that is here is anyways very interested in any kind of GR effects when we are thinking about objects that are very close to the neutron star or the black hole. Then you have strong gravity. And when you have a neutron star, it's even more interesting because then you have a hard surface, so you can actually see emission directly from from the surface, which has then relativistic beaming and all these kind of interesting effects. But the point that I would like to add, and it was not too much mentioned before, is the connection to the spin. This is a very long story. There was a lot of excitement in the beginning when first killer QPOs were detected, that if you look at the frequency separation of the two killer QPOs, then this looks like it was connected to the spin. I would like to show a plot here from, I think, what is now up to the date, from the latest paper from Diego Altamirano et al. Most of the sources are here on this plot. Most of the sources actually know the frequency. So this is the frequency separation of the two killer QPOs over the spin frequency versus the spin frequency. It would be very nice to know if there is a connection, because if we know the spin frequency, we can infer a lot of other stuff about the equation of states. So how does it look like now? In the beginning, there was some excitement because the frequency separation of the killer QPOs seemed to be about the spin frequency. That would be really exciting, but eventually it turned out that this frequency separation also varies. And it turned out later that this frequency separation could be also half of the spin frequency of the neutron star. Eventually, with many more data coming up, you could see that this line would be the spin frequency, the frequency separation of the two killer QPOs, if there would have been no correlation at all. It would be just a fixed number, 300 Hertz, I think this is. Actually, it looked like it might not be too far away from the truth, but then there was also another source discovered by Altamirano et al., this J17511, where the frequency separation is now again half of the spin frequency of the neutron star. So it looks like it's far away from the behavior of the other sources, and it's also not what might have been suggested as a step function. So there is no clear answer at this point. It looks like there is a connection. There's many sources that have exactly half the spin frequency of the neutron star as a frequency separation, or either half or one of it. But there is no clear physical model what would cause this to be one or half of it. But anyways, if we could make this connection, I think this should be one of the goals of all the models. We could get information not only for X-rays, but also for gravitational waves. And I put this plot up to remind us that we are not only working in X-ray astrophysics, but in general, you can also use these results for gravitational wave physics. And I know many people might get goosebumps if they hear now about gravitational wave missions, but this is about ground-based ones, so we're not competing now with LISA or something. This is actually this is from an older paper from 2008 from Watts et al. that if you know the spin frequency of some of the kilohertz QPO sources, you can get amplitudes in gravitational waves that are detectable with advanced LIGO. So it would be really good if you could get this connection of the kilohertz QPOs with spin frequency. So I had to put up a slide for Sinus X1, even though this is quite an old paper of ours from 2006, because it still attracts a lot of attention, and a lot of people, including the group here, are working on this. So I would like to summarize, see what of the aspects are still valid. I mean, what do we still have to use from those observations? What you see here on the plot is the frequency separation of the 2 kilohertz QPOs. I mean, the frequency difference of the two versus the frequency of one of them, the upper kilohertz QPO, and the blue points are our observations, and these are older observations from Stratos Boutloukos et al. So what are the key aspects? Okay, we still see that we have very low kilohertz QPO frequencies. So if you hear the term kilohertz QPO, you would think of something that is of the order of a kilohertz. Now this is not really the case. I mean, we're talking about frequencies that are down to 50 or 250 hertz. But this is still the same class of frequencies, the same class of QPOs, because they follow very nice relationships with other frequencies. So they're established in the same class, but they go very down to in frequency. So whatever model we have to explain also how it can be so low in frequency. The other key aspect is that you have frequency separation of the two very low. So usually you see most of the sources have frequency separation of something like 300 hertz, and this was also in the previous slot where you saw that there was a suggestion that maybe the frequency separation is just the same for all the sources, something like 300 hertz. But in this case you have something that's very, very low, although we don't know the connection of the spin, but it has a very low frequency separation. The record holder now is J1751, the IGR source from Altamirano et al. That has a frequency separation of under 20 hertz. There we also unfortunately don't know the spin yet, or yeah, anyways, it will be very, very, very much low in frequency over here. Another key aspect, and quite unique, is that you have the frequency separation varying by very much. This is a frequency separation varying by 180 hertz. So whatever connection you also want to make to the spin, this is very crucial because you cannot obviously change the spin by this. So there's some other connection. Whatever model you have to do, you have to think that this frequency separation also is allowed to vary. Now, you also see that it varies quite monotonically, and this was very tempting, and also in the original paper from 2006 we had plotted two lines over here, and I removed them from this plot, and I will explain why. Basically, yeah, you can draw also a straight line. It will be in simple resonance frequency of a simple relation of two resonance frequencies. Or there were some lines predicted by the relativistic precession model. At that time it was the precession model by Stella and Bietri, and by now it's been extended by, among others, by Torok et al. I think this will be part of the next talk, or the last talk of this session. But what I want to point out here, and that's why I didn't put the lines here, that you have to be very careful when using those relationships. I mean, on the Stella-Bietri model it was a little bit more simplified, but also in the Torok et al. Paper you're working in near Kerr limit, and I will show in some figures later about what we have worked on. But the most important thing I want to say here is that this is just the frequency. I mean, most of the models are looking at the frequency, and you heard also in the previous session that it's not just the frequency that you can measure, that you can use from observations. I mean, it's the most easy thing to think about when you think of oscillation, but there are so many key aspects that you also have to model when you have a model, and this is what I want to go to next. So what are other key observations do you have? I mean, okay, so Sinus X1 in that aspect is not too unique. I mean, the frequencies are very unique, but there are other sources that show typically coherences that is of 0.005, so quality factors like what Mariano was showing half an hour ago, that go up to 200 or even more. So it means that you have an oscillation that's very coherent. It doesn't change very much of a frequency. Plus you have amplitudes that can be very high, can be like 15% RMS. So how can you use this into your modeling? I mean, if you think about it, what does this coherence mean? I mean, you have the nice toy model that we heard earlier, but if you just try to implement it in a toy model inside the disk, what would be that? So it means that you have a frequency of the spread of the frequencies would be so narrow, so delta nu over nu will be so narrow, and it will be related to the change of the radius of this annulus where you're supposed to get the frequency, if that will be in the disk. It will be of the order of the same order of magnitude. Now, if you multiply this also with the luminosity of the disk, and you know that the luminosity of the disk is just maybe a fifth of the luminosity of the total luminosity, if you include also the luminosity of the star, that means you will get an RMS amplitude. If you had all this luminosity coming from this annulus of the disk, it will be at the most about 0.1% RMS. Now, I said we have radial amplitudes observed from many sources that reach up to 10 and 15% RMS, so we're talking more than an order of magnitude difference. So it means that it's very difficult, I mean, even if you have a matching frequency of some oscillation in the disk, in an annulus of the disk, to give you such a high amplitude, because you observe so high amplitudes. So this is, I think, something that should be used when we consider modeling, and not just the frequencies. Now, how can we actually get the amplitudes as high as we observe? I think, and there's many papers on this series, that the easiest way, and maybe the only way to do it, is by getting the emission directly from the neutron star surface. I mean, if you have something oscillating in the disk, it's very difficult to make it so strong. But if you have something like a clump in the disk that falls, because this is the inner edge of the disk, and falls to the neutron star surface, then all this matter will be falling there, and it's being heated up and emitting in X-rays in much more powerful way. It happens to be that the frequency of this orbit is exactly the same frequency of the imprint of this hotspot. So this is an old idea from my former advisor Lamb in 1998. In principle, if you have a clump of the inner edge of the disk and it falls, the way this pattern of emission will move as this thing rotates is exactly the same frequency, with some variation because of the finite time it takes to drop on the following neutron surface. So this is one thing, one way to get this. And another argument for the accretion-powered origin is that, well, I mean, obviously the same range of frequencies are also in the ones that you observe. So it would be easy to match. Plus, the frequencies vary also by a lot. So if you have something in the inner edge of the disk moving in and out, it will also cause the oscillation to move in frequency. Plus, we also heard earlier this morning by Didier that you can also look at the spectra, and the spectra also suggest that it's not something at the disk, but the emission is coming from the neutron star surface or from the boundary layer. Now, these are the arguments for the origin at accretion power, but there is also problems, and one of them is also from the observations from the sinus X1. If you get frequencies that are as low as 250 Hertz, means that you have to have the inner edge of the radius being of the disk being a radii of something like 50 kilometers. Now, this is obviously very difficult to make the magnetic field connect so far, and this is one of the challenges if you want to have the matter being funneled through the magnetic field. So I will put this as an open question: can the magnetic field still be so strong? I mean, they're so far away. I think maybe there's more evidence coming from the sources that now we start appearing also in radio waves. So this is still an open question. Now, what can we do now? Maybe we can find a connection to lower frequency QPOs. I mean, there's I think too many open questions into the higher frequency QPOs, the killer QPOs, but maybe we can find a connection to the lower frequency QPOs. Why? Well, for one thing, it's because we have much better count statistics. You have more time to accumulate. I mean, you have more photons. So in principle, you get a stronger signal. And there is also some evidence, although so far I was only talking about neutron star low mass X-ray binaries, but there might be also something about QPOs in low mass X-ray binaries with black holes, as well as AGNs and ultraluminous X-ray sources, where there appears to be similar QPOs as the ones that we observe in neutron star low mass X-ray binaries. But going back to neutron stars, maybe the most challenging observation recently was the one that Diego presented yesterday about the source in 2005, X2, where we saw that the QPO, the low frequency QPO, the HBO, seems not to agree with the lens steering model. And this is the plot from their figure, and also what was shown yesterday. So what you see here, I'd like to repeat it to compare also with this figure, is the frequency of the oscillation, of the oscillations versus the radius. And here this line would be the orbital frequency, this will be the periastin frequency, and this will be the nodal precession frequency, the upper bounds of the nodal precession frequency. And this gray line is the observed kilohertz QPO frequency, and this is the observed HBO. So what was hoped to be the nodal precession frequency. And you see that the numbers are too far away, so seem to exclude lens steering precession. This is work with George Papas that we did. This is from a paper from 2012, where he shows the same lines. Basically, I tried to put this so that they match roughly in the ranges, although there's also some factors there of the mass. But I mean, you get the same picture. This will be the same precession. This will be the orbital frequency. This will be the periastin precession frequency, and this will be the nodal precession frequency. And what I would like to point out here is there's some deviations depending on how you describe the space-time. So in most models so far, a Kerr space-time was used. I mean, in these papers, the Markov equation were used by taking the 4 first multiples after you produce numerically the neutron star with the RNS code. And this deviation started appearing when you get a neutron star mass that is lower than, let's say, the typical ones that you might expect, like 2 solar masses. I mean, this would go like 1 to 1.4 or something. So obviously this doesn't go the right direction. This goes to lower frequencies. So it's not. I mean, there's no way to explain such a high frequency as nodal precession. But what I want to point out here is that there is deviations from the simple picture that's been developed, and I think there's still work in this direction. And I also have to mention this. So this line is for a neutron star rotating faster. So this is about 100 hertz. So it's not supposed to be compared with the 2005, which is rotating 11 hertz. But again, the point here is that there is more into physics than the simple descriptions. And well, it still doesn't look like we can explain QPO frequencies with a lens steering model at low frequencies, but it means that maybe there is more physics that we have to put into there. And my thinking is that he has to go into physics of the disk. So maybe we have to look back at the magnetospheric bit frequency models. So the last slide is maybe a controversial one, especially with a lot of observers in the audience, is that maybe we have to be also a little bit more careful about the quality of the observations. So please bear with me. I mean, the argument I want to make here is not that everything that we have out there is controversial. What I want to say is that maybe we have to be a little bit more careful when we look at the data until we get better data. So obviously, we hope for loft, and then we will resolve all these questions, but this will take still a few more years. But with the observations that still exist now, it is, we have to know that there are a lot of assumptions going into the modeling and into the observations that we have to know, like the background, Poisson noise, sometimes just arbitrarily shifted up and down, added shift techniques, and still many of the observations is just above 3 sigma. And we know of many sources of many observations, like the most high 1330 hertz that has not been confirmed. So do not try to fit all your models with existing observations. I mean, there might be some intrinsic ambiguity there. So I think I would just leave up the conclusions with what is the state of the art now and what we think we still have to pay attention to, not just the frequency. We have to look also at a lot of things. Didier mentioned also this morning, and I mentioned a few more today, like the time lags, like the spectra. You have to look at the coherence and the amplitudes, and you have to explain how the frequencies vary by so much, and also how you can have such a narrow range of radii producing such strong emission. Thank you.